So molecular orbital theory is the final topic in chapter 10. Um, and it too, like valence bond theory, is based on the quantum mechanic theory. And that means that we are taking into consideration where those electrons reside in the atom or molecule. We've discussed diamagnetic and paramagnetic characteristics. Paramagnetic molecules or atoms have unpaired electrons. In diamagnetic molecules or atoms, all the electrons are paired. And if we look at the valence shell electron pair repulsion and Lewis structure theories with respect to the O2 molecule, it appears to us that all electrons are paired. So it should be diamagnetic. However, it is paramagnetic, and this has been shown experimentally. Thus, the creation of molecular orbital theory. So this theory also combines pure atomic orbitals, similar to valence bond theory, but in a slightly different way. The bonds formed from the interaction of atomic orbitals actually form what we're going to call molecular orbitals. Okay? So while valence bond theory doesn't explain magnetism, molecular orbital theory is designed to do that. Okay? I do want to point out, though, that molecular orbital theory does not describe geometries, but it does provide a model of bonding that explains magnetism. So this isn't quite as complex as it might seem, and you will learn how to fill in a molecular orbital diagram. But in contrast to the localized bonding and lone pairs of electrons of valence bond theory, molecular orbital theory describes the electronic structure of molecules in terms of molecular orbitals, which may spread over several atoms or the entire molecule. So these are owned by the molecule, so to speak. In molecular orbital theory, pure S and P atomic orbitals in the molecule combine to produce orbitals that are spread out over the entire molecule. And these are the new molecular orbitals. So we're also going to look at the fact that, similar to valence bond theory, that the number of molecular orbitals you get by combining pure atomic orbitals has to be the same. So, for example, in this diagram, we have two pure atomic orbitals, and we're going to say this is a hydrogen atom, or the hydrogen atom, each with one electron. And these pure atomic orbitals are going to combine and form two molecular orbitals. One is of lower energy than the pure atomic orbitals, and the other is of higher energy. And the lower energy orbital is called the sigma 1s bonding orbital. The orbital or molecular orbital with higher energy is called the sigma 1s or sigma star 1s, which is the anti-bonding orbital, and is less stable. Remember that there is a desired or a threshold for a minimum amount of energy when two atoms form or create a bond between them. So the way this is described with respect to the interaction of these orbitals is either a constructive interaction in which the electron density congregates between the two nuclei, allowing or promoting the formation of a bond, or a destructive interaction in which there's this planar node between those two nuclei, and the electron density is on the outer edges of those of those orbitals coming together. Let's just put it that way. So if we have two electrons, as we do in the sigma 1s bonding orbital here, we are going to form that HH bond, or a single bond between hydrogen. Now, if we were looking at another element and the anti-bonding orbital was also filled with electrons, because we had more, we aren't dealing with hydrogen anymore, there would be no bond formation because the anti-bonding orbital is going to cancel out the bonding orbital. And we'll look at a diatomic helium molecule to demonstrate that. So we have bonding molecular orbitals that have lower energy and greater stability than the atomic orbitals from which they were formed. And we have the anti-bonding molecular orbital that has higher energy and lower stability than those atomic orbitals from which they were derived. So I'm not going to be having you write electron molecular orbital configurations this semester. However, we are going to go through this list because it also describes the filling and the rules that apply to molecular orbital diagrams. So the number one, the rule of the number of molecular orbitals formed is always equal to the number of pure atomic orbitals combined. This is the same as in valence bond theory. Remember, the number of orbitals we combine to produce hybrid orbitals is always the same. The more stable the bonding molecular orbital, the less stable the corresponding anti-bonding orbital. And this, remember, the more stable bonding orbital has less energy than the anti-bonding orbital. We're going to fill molecular orbital diagrams from low energy to high energy. So bonding orbitals are going to fill before anti-bonding orbitals. Same as filling an orbital diagram. Each molecular orbital can accommodate up to 2 electrons with opposite spins. We are going to use Hund's rule when adding electrons to molecular orbitals of the same energy. So that means we're going to put 1 electron in each orbital, molecular orbital, of the same energy before we start pairing those electrons. And finally, the number of electrons in the molecular orbitals is equal to the sum of all the electrons in the bonding atoms. Now, when we're working on some of these molecular orbital diagrams, the bonding may not be occurring in the lowest energy level, and so we will only focus on those valence electrons. So this is a molecular orbital diagram, and this is for Li2. So a diatomic lithium molecule. So lithium has a total of 3 electrons. Its atomic number is 3. So each lithium atom has 2 electrons in the 1s and 1 electron in its 2s orbital. So when the 1s orbitals combine, we get our sigma 1s bonding orbital and the corresponding sigma antibonding 1s orbital. We combine our 2s orbitals to form the sigma bonding 2s and the antibonding sigma 2s. Okay, so we have 3 electrons here. So we have a total of 6 electrons we need to distribute in our molecular orbital diagram. We start with the lowest energy, putting 1 in, well, actually 2 in the 1s, 2 in the 1s antibonding, and then we will have paired electrons in the sigma 2s bonding orbital. So I already told you that these cancel one another out, so that lower energy level does not participate in bonding. These are the valence electrons for lithium. So that single bond for lithium comes from that 2s sigma bonding orbital. Okay. So maybe I'm going to call this no net bond. And this is where our sigma bond is coming from. So we will be also using p orbitals, and there are 2 possible interactions between equivalent p orbitals, and we see those here. There are, for each type of interaction, and we've already seen this essentially when we looked at hybridization theory. So we have 3 p orbitals, 2px, 2py, and 2pz. And the top part of this diagram is describing what's occurring with the 2px orbital. And those interact head to head. Okay. And so in the constructive interference, we have the electron density between the 2 nuclei, and we form a sigma 2p bond. Okay. So we've got 2px from 2 different atoms, like atoms, that combine and form similarly a sigma 2p bonding orbital and a sigma 2p antibonding orbital. Okay. Destructive interference, again, you're going to have that planar node between the 2 nuclei and no electron density. Electron density will be out in this area, and thus no bond formation, or very unstable, I should say. For the other 2p orbitals, 2py and 2pz, when these combine, this is only showing one. We could have had another box here, so we show both of them. But they both do the same thing, and you'll see what I'm talking about when we actually start filling a diagram in. Similarly, we saw pure 2py, 2pz orbitals in valence bond theory that were utilized to make a double bond. And so these are interacting side by side, and we get that electron density above and below the nuclei. If this is destructive interaction, we're again going to have that planar node, so there is no electron density between the nuclei, and that is the antibonding orbital. All right, so here is what I was talking about when I referenced that we could have had a second box there. Here we're putting all three of the p orbitals together, and we're gonna, this could be the nitrogen atom, for example. We're not using electrons here though, but we have the three p orbitals, and when they combine to form molecular orbitals, we're gonna get pi, 2py, 2pz, and I might not have said pi on that previous slide, sorry if I didn't, and a sigma, 2px. You'll note that the sigma 2px has higher energy than the pi, 2py, 2pz. You're not going to be responsible for, because this will change when we get to looking at oxygen or diatomic oxygen and fluorine. If need be, you will be given the proper orientation of these orbitals. But they too have their corresponding anti-bonding orbitals up here at the top. All right, sorry this was already filled out more or less, but we can use the number of electrons in bonding orbitals and anti-bonding orbitals to predict the bonds that will form between two atoms. And we do that by subtracting from the number of electrons in bonding orbitals the number of electrons in anti-bonding orbitals. Okay. So essentially, this is a similar concept to valence bond theory with respect to the number of net bonds, but bond order in molecular orbital theory can be either 0 or negative. And if it is 0 or negative, there is no stability and that bond will not exist. We can have fractions. They are as stable, obviously, as a half a bond isn't as stable as a whole bond, but it is a possibility. And we can also predict strength based on the order of that, the size of that bond order. Okay, so here we're comparing H2 to H2 plus, and then we'll look at helium, the diatomic helium molecule or molecular orbital diagram, and predict whether or not that will exist. And we do know that noble gases are relatively inert and do not interact with other atoms. So this is basically proof of that when we calculate this bond order. So for the H2 molecule, each hydrogen has one electron, and we combine the 1s orbitals. We have the sigma bonding 1s, and we have the sigma anti-bonding 1s. This one is filled. When we calculate bond order, it's 2 minus 0. So divided by 2, I might not have mentioned that. You have to multiply or divide by 2 up here. So we get a single bond, which is what happens in diatomic hydrogen. If hydrogen, that H2 molecule, should lose one of those electrons, then we have only one electron remaining in our sigma 1s bonding orbital. And that produces half a bond. Okay, so obviously this isn't very or as stable as the H2 molecule, but it can fleetingly exist. And now looking at helium, diatomic helium, we have filled not only the sigma bonding orbital, but also the anti-bonding orbital. So there is no net bond. And if we calculate bond order, we get 0. So this does not exist. However, if the He2 molecule should lose an electron, so we've lost one of those electrons in the sigma antibonding orbital, now we have a bond order of 1/2. So, while not very stable, it is something that could happen. Oops, guess those were all there. All right. So we've already looked at the Li2 molecule, and what I forgot to mention when we were looking at that orbital diagram, both electrons are paired. You can go back and take a look. So that would have been a diatomic molecule. Remember, molecular orbital theory's purpose is to explain magnetism. Next, we're going to look at B2, so diatomic boron. Boron has 3 electrons, so each boron atom has 3, so we have a total of 6 electrons to distribute. And we're going to start again filling from lowest to highest or molecular orbitals with respect to energy. So that's 4. That means we have, whoops, lost my pen there for a minute. We have 2 unpaired electrons in the 2p pi orbitals here. So this would be 2py and z, and this is sigma 2px up here. So now we have unpaired electrons, so that means that this is a paramagnetic molecule. And when we determine bond order for this, we're going to count once again the number of electrons in bonding orbitals, of which there are 2 plus 2, or 4. And we're going to subtract the 2 electrons in the anti-bonding orbital, divide that by 2, so we get a bond order of 1. So we'll have 1 single bond created here. Now let's look at C2. Each carbon atom has 4 valence electrons, so we have a total of 8. Again, we start filling our molecular orbitals, filling equal molecular orbitals of equal energy, 1 in each, before we start pairing. And in this case, all of our electrons are paired. So this will be diamagnetic. And our bond order will be 2. So we have 2 plus 4, 6 minus the anti-bonding electrons, giving us a bond order of 2. So we will have a double bond between those 2 carbon atoms. But please note that both of, in contrast to valence bond theory, these double bonds are made by pi 2p orbitals, not a sigma and a pi. Whoops, sorry, I didn't mean to write. Oh, I meant to make that a carbon here. Next is N2. Nitrogen has 5 valence electrons, so we have a total of 10 to distribute in our molecular orbitals. and 2, 4, 6, 8, 9, and 10. So this would be also diamagnetic. All electrons are paired. And our bond order will be 2 plus 4 plus another 2, which is 8 minus 2 divided by 2, gives us a bond order of 3. So we will have a triple bond N here. So in this case, let's see, looks like we will have a sigma bond and 2 pi bonds. No, whoops. I think that might be two of the same page, which, oh, yeah, actually it is. Sorry about that. I don't know if the right one is on here, so I think that what I'm just going to do is we're going to eliminate this, and I'm just going to modify this because there is a change in the order of the molecular orbitals once we hit O2 and F2, and I'm not sure it's on the next page, so I don't want to flip forward just in the event I don't have the right one here. And I'm gonna relabel these. Let's see. So we have our sigma 2s bonding, anti-bonding, and now we have sigma 2px, and then our pi, whoops, pi, 2py, 2pz, and these are the bonding orbitals, and then their corresponding anti-bonding orbitals, and this would be the sigma 2px. So the change is just here, and that applies to O2 as well. So oxygen has 6 valence electrons. So we have a total of 12 here, filling our molecular orbital diagram. And 2, 4, 6, 8, 10, 11, 12. So this is what explains the magnetism of the O2 molecule. This is paramagnetic. Bond order is going to be 2 plus 2 plus 4 or 8 minus the anti-bonding electrons, of which there are 4, divided by 2. So we have a bond order of 2, which corresponds to an OO double bond. Now with fluorine, 7 valence electrons, we have a total of 14. All electrons are paired, so it's diamagnetic. Bond order here is 2 plus 2 plus 4, which again is 8, minus our anti-bonding, which are 2 plus 4, to 6 divided by 2 equals 1. So single FF bond here. I'm sorry I couldn't blow this up a little larger. I tried. Oh, and I just flipped it forward. Sorry, so I'm going to have to do this by hand. We're going to look at an